Okay, great. So thank you very much for giving me the opportunity to talk about my D3R results from stage 2. And yeah, this is like an example of how we apply affinity prediction methods in industry and what challenges we face there and how that also reflected on the D3R challenge. So affinity prediction has gained a lot of interest in the pharmaceutical industry and also at Merck. And well, this has gone back a long time already to the 90s, where people started building QSAM models and then moved on to docking in the 2000s. And now, since the 2010s, we think that free energy calculation methods have really become mature enough to be also used in an industry setting. And so the idea of my postdoc that I'm currently doing at Merck in Darmstadt is to explore the opportunities and the challenges of using free energy perturbation in real-life drug design projects and explore both the opportunities but also the limitations of the method. So in such drug design projects, we have like different requirements. So it's very important to have an accurate method that can correctly rank the compounds and help to the medicinal chemists to prioritize them for synthesis. On the other hand, we also have to have a fast method. So many people don't want to wait for weeks and weeks and try different setups to get their results. So speed is obviously very important. And also, and maybe more than in an academic setting, usability is a big issue. It's important to have an automated protocol that's easy to set up, that can run with relatively low efforts, and therefore we need to rely on a commercial protocol which is highly automated. And for this, we at Merck here use the Schrödinger FEP Plus. However, on the other hand, relying on such a commercial protocol also has the downside that you also have to rely on the testing by the vendor, and most of the performance records are, of course, also published by the vendor, and there's little opportunity to compare those commercial protocols to other protocols that are used in the field. And of course, this is also very desirable to see how accurate the method is, this highly automated method is compared to other methods, and also to independently be able to validate it. So, and that's why I took this opportunity to participate in the D3R challenge. Due to time constraint, I only participated in stage 2, where crystal structures with the binding mode were available for both free energy prediction sets. This also corresponds well to the situation we face here in our day-to-day projects at Merck. And it's, of course, a great opportunity to be able to participate in such a community-wide prediction challenge that also uses data sets of proteins and drug-like compounds in contrast to other benchmark sets that use for like host gas systems or other things. So we were very happy to have this important opportunity to independently validate the method we use and how we also use it here, and compare this commercial protocol to other quantitative affinity prediction methods. And also, the reason for only participating in stage 2 was also that I have to do, of course, a lot of other projects, work on in-house projects. And there was actually very little time for me in January to complete this challenge. Actually, I had to do it very last minute. I just set up the protocol, got the results, and submitted them right on the last day. And actually, this comes very close to the situation we often face in our projects here, so to real-life drug design. So what I did was I took the proteins, I selected those crystal structures that contained ligands from the 2 free energy prediction sets. I generated the ligand conformations from SMILES, and aligned them to the reference X-ray, and if necessary, generated additional force field parameters, and then used the Schrödinger FEP Plus calculations as is, and ran those calculations on a GPU cluster with default settings. And that means that for this in the free energy perturbation protocol, every window was run for 5 nanoseconds. So these are the results for set 1. We obtained reasonable RMSE. So I calculated this with our in-house tool, so it's a little bit higher than what was calculated with the tools from the D3R team. However, there was like no predictive power in terms of ranking. I have to say, for the setting up, I considered I put all the ligands in the same map, and I assured that there was no charge change, so I artificially added a proton on this carboxyl group of compound 101. What is interesting about this bad ranking performance is that it's also something you would expect within the normal errors on such experimental data and the prediction accuracy you can normally expect for those methods, and that would give you an expected R2 of 0.19. So actually, this this poor ranking performance is not so surprising. Still, the method correctly predicted the sign of delta G in 13 out of 14 cases. In the second set, we also achieved a similar prediction accuracy in terms of RMSE. However, here, due to the distribution of the data in this affinity set, also the ranking was a lot better. For this setup, we again assumed that all ligands carry the same net charge, carry a neutral charge, which in this case is actually affects more of them. And I also I took both binding modes that were observed in the X-ray and created for every ligand, if it was applicable for this type of ligand, I created both alignments to the reference X-rays and then used also both of them to calculate the free energies, and in the end chose the free energy change that was predicted to be more favorable, and that was what I also submitted in the final prediction. The RMSE we observed for both data sets was within the range of the accuracy we also observed for other projects, also in-house and also on public data sets. Was maybe a bit higher than what we usually expect, so I turned to look at those data in a bit more detail to see if there was any particular reason for that. So the quality of the simulations looked quite good. The protein conformation was found to be stable. So here are some examples for the protein RMSE over those 5 nanoseconds. However, when I looked into the ligand RMSD, I found that for some ligands, there were actually RMSDs that are observed in higher than those that are usually observed. And especially when you now looked at the convergence of the simulations in the protein ligand complex simulations, I saw that actually this, many perturbations were not really well converged, whereas simulations in solvent appeared well converged. So it seems that actually, due to those time constraints, I didn't run this multiple times and I didn't check that before submission, but it seems to be very likely that those simulations are not yet converged, and extending the simulation time beyond 5 nanoseconds per window should improve the sampling and hopefully also improve the prediction accuracy. And this is something I'm going to explore now in the future and see if that would really help to improve these results further. So in total, we saw that the current protocol we use for setting up and running FEP calculations with Schrödinger FEP Plus at Merck is comparable to state-of-the-art affinity prediction methods, and that's a really great result for us for participating in D3R. We also found that FEP Plus is a robust technique. There was another group that also participated with the same method in D3R challenge stage 2, and the results were virtually the same. So the human factor in setting up those calculations of such a highly automated protocol seems to be negligible. For us, it's very encouraging to see that FEP calculations can be performed to sufficient accuracy even when we are under high time and resources constraints that we usually are in our drug design projects. However, on the other hand, you can also see that the default settings using just 5 nanoseconds per one window is probably not enough, and more sampling will often be needed to achieve higher accuracy. In total, those results from participating in this challenge give us confidence to further apply FAP to other targets in our ongoing drug design project, and also extend these applications to larger library screens. So instead of just looking at sets of 10 to 30 compounds, we really want to move affinity prediction further and screen larger libraries of hundreds of compounds. So in the end, I would like to thank all the people that helped us to set up FAP at MEC. So especially the application scientists from Schrödinger, Daniel Kappel and Thomas Steinbrecher, and everyone at the computational chemistry and biology group. Thanks for your attention.